going to start my recording now. All right, so let me see if I could share my screen here with you all. All right, so you can see my screen now, and
yeah.
All right, so we're starting with this particular slide here. All right, that's the slide that we had before. So we're heading into hydrocarbons, and there are various ways in which you can separate hydrocarbons. Now we have to look at the sources, and as you can see, on this particular slide, you're seeing a fractional distillation. So this will kind of tack back on the area that we would have done, which is with mixtures and separation. And you would have remembered fractional distillation being a process by which we separate miscible liquids into different fractions, all right, based on the boiling point. So if you notice here, we have different hydrocarbons. Well, what the source is basically that it came from is petroleum. So we can have crude oil, which is one of the main sources, and we could also have natural gases, which are sources of hydrocarbons. So now, here is it. We have when you collect the crude oil, what's going to end up happening is that you place it into this fractionating column, but these really large ones in the industrial process. As you can see over here in the corner, this is a picture of how the columns would actually look in the industry. So what happens when they drill and they collect the crude oil, they're going to place the crude oil into these fractionating chambers, and under extreme temperatures, they're going to be able to heat them. And what's going to happen, the hydrocarbons between 1 and 4 in length, carbon chains in length, they are going to be at a lower boiling point. So they're going to evaporate faster. And as a result, they're going to go up to the higher point in the fractionating column. All right. So what happens, they're going to be leaving as gases. The others that will have lower boiling points, they're going to condense at different points within the fractionating column, because within the fractionating column, the air is actually cool on the top, but the temperature that is at the greatest is the one at the bottom. So what is going to end up happening, if you notice here, we have C5 to C9, which is naphtha. These fractions of these hydrocarbons, they're going to condense and they're going to be collected at these levels. Then we have gasoline, which is our next hydrocarbon, which is going to be coming out in the fractions in the fractionation of petroleum. We're going to have all of these actually coming out within the fractionating column at different levels. All right. So depending on the boiling point, which is based on the length of the carbon chains, we're going to see where they're going to come out. And in the diagram, we're going to see the uses that we can have. So hydrocarbons between 1 and 4, we could use them in gas, in LPG gas. That's what we use to cook. Example, propane. Some of the other chemicals like gasoline, which is from C5 to C9, you will hear this word octane levels, and these things in petroleum, they try to have low levels of octane, which is an 8 carbon chain hydrocarbon. These are in the areas of petrol in vehicles. Then we also have jet fuel, and the list goes down to diesel. As you start going down, the viscosity of the hydrocarbon changes. Now, how do they actually cause the separation? This is one fractionating between the hydrocarbons using fractional distillation. by carrying the hydrocarbon under high temperatures, they can be able to separate the different hydrocarbons found in crude oil, all right, or petroleum. Okay, so in natural gases, these are another source you can get, which is the same from drilling, but when they get these natural gases, they are of the shorter carbon chains. So they would be in a gas form, and you can be able to collect them, and you can carry them through different processes as well. Now, there's another process in which you can use, and we call this catalytic cracking. All right, so cracking is another method, but this method particularly is anytime you have hydrocarbons with long lengths, really, really long lengths, and you want to get shorter carbon chains, you can carry it through a process called cracking. So what cracking does, you have two types. You have one that is called thermal cracking, which you use, extreme temperatures, and we're looking at above 700 degrees Celsius. And in addition to that, at about 70 atmospheres. So imagine our atmosphere here, and they're increasing that pressure 70 times. So the temperature is going to be above 700 degrees Celsius. The atmosphere is going to be about 70. And what that does, the pressure breaks the molecules, especially long chains, breaks them into smaller chains. And when you have the smaller chains, you're going to develop smaller hydrocarbons. But in the breaking of those chains, the type of hydrocarbons that you form are actually alkenes. So the alkenes are going to be formed, and we could see a nice example of these here from the same cracking. Now, in order to make cracking a little bit easier, here's the temperature, 700 degrees Celsius and 70 atmospheres. What's one of the things that they actually do? You can use a catalyst. So there's the second cracking, which is called catalytic cracking. And in catalytic cracking, you use a catalyst. All right. And by using a catalyst, if you could remember, well, I don't know from your biology or whatever areas you would have learned before, a catalyst is a substance that can either speed up or slow down a reaction. So by placing a catalyst into this particular reaction, you could cause the reaction to become faster, or you could get the reaction to become slower. As a result, you can decrease the amount of energy that you need in order to carry out your reactions. So, example, thermal cracking, all right? So thermal cracking will include what we have here, 700 degrees Celsius to 700 degrees Celsius in order to break the long carbon chains. If I add a catalyst, an example of a catalyst is aluminum oxide, okay, which now can help the temperature to decrease to 500 degrees Celsius. So and instead of going to above 700, I could use 500 degrees Celsius and cause the cracking of my particular hydrocarbon, all right? So as you can see here, modern cracking using zeolites as a catalyst. So another catalyst, zeolites, are examples of the types of catalysts that you'll use. So the types of catalysts we use are called zeolites. So what is an example of a zeolite? The one that I talked about. Aluminum oxide is a zeolite, and silicon dioxide is also a zeolite. So you could use any of these in catalytic cracking in order to break the bonds within a long carbon chain. All right. So let's see if we could tap across here. So now, what petroleum really has in it? When you get a barrel, and this is a barrel of petroleum, all right? So we're looking at, this is what? How much gallons, boy? Can't remember how many gallons, but I could think I could add them up on the side here. 1, 2, 3, 4, 5. All right, so above maybe above 40.
Come on, you think you need some
Right?
password.
Approximately there. So what happens inside of crude oil, which we refer to as petroleum products, where we get petroleum products from? We can have gasoline, you can have diesel, you can have waxes, you can have boilers, asphalt, so on and so forth. But the levels, it shows how much petroleum has. And the majority of petroleum is actually made up of gasoline. So remember, we said that the crude oil, which is what I'm referring to being as petroleum, is made up of different chemicals that combine together. And these chemicals that combine together form a miscible mixture. All right. I see the rain is falling. I don't know. You all hear me clear, right?
Yeah.
Yeah.
All right, good, good. So now let's go on. So we have this concept called unsaturated and saturated compounds. All right. So we're not going to focus on the one as optical isomers and structural isomers, although we know about structural isomers already, and we wouldn't go into optical isomers because that's not for this level. Okay. So what we're looking at is differentiating between hydrocarbons. To differ between hydrocarbons, we differ them based on the number of bonds that they have. All right. And as well as, if we go even more, we sometimes we look at the homologous series. But in general, when you are separating organic compounds or these hydrocarbons, they are separated into two groups. You can either have one that is saturated or one that is unsaturated.
Excuse me.
Uh-huh.
Where in the concise is this topic located?
In the concise. All right, let me see if I get my glasses.
Thanks.
It will be at the back. So the topic that we talk about, 134, which is crude oil and natural gas, 134, and we talk about cracking, which is 135.
Okay, right, cool. Thanks.
All right. Okay. So those explains the two different cracking. Now we're looking at the difference between hydrocarbons. So you can move on to page 137, and you will see saturated and unsaturated in the concise, that is. All right, so what is an unsaturated hydrocarbon and a saturated hydrocarbon? Very simple. A saturated hydrocarbon is basically a hydrocarbon that has single bonds throughout. Okay? So when we're talking about single bonds, carbon to carbon single bonds. And if you remember, just asking a question, just for so, what type of organic compounds do you know that are carbon to carbon single bonds? Just asking you the question.
Alkane.
All right. An alkane, right? That is correct. So alkanes are saturated. All right. If we can bring it to something that we know naturally, sometimes you hear about saturated fats. So you go to the grocery or you have a snack and you look at the back of the pack and you're going to see different types of fats. You're going to see trans fats, you're going to see saturated fats, and you're going to see unsaturated fats. This is just by the way, the saturated fats are the ones that we try to keep away from or limit less, even though we need them in our diet. You want to have them at low amounts, but the unsaturated fats is the ones that we want to have greater amounts of. All right, because they help us to make good cholesterol. But that's just on the other hand. Unsaturated compounds are the ones that have double bonds and triple bonds inside of them. So a carbon to carbon double bond or a carbon to carbon triple bond is an unsaturated compound. And that's how we identify them. Okay? So I'm just tapping across here now. All right, this table just shows the different boiling points between the hydrocarbons. So you can take a look at that if you want the freezing point and the boiling point, and to at least understand where in the fractionating column they are going to come out based on the number of carbon chains. Now, just tacking back a little bit, since we're on this note, Remember, one of the physical properties of organic compound is one of the characteristics, as the number of carbons increase, what would change?
Number of hydrogens.
Right, that's going to think, but we're looking at physical property. As the number of carbons increase, and you can observe it here, what you are seeing happening, what changes as the number of carbons increases?
The boiling point.
Right, that's correct. The boiling point is going to change. All right. Why is that? Because the molecular weight is going to change, and the forces of attraction between the elements, between the molecules, are going to change as well. So as a result, it's going to, the boiling point is going to increase. All right. And we know as we increase in the number of carbons, the physical property changes. So we look at, and I think we're going to touch on it again when we go into the next slide, the next PowerPoint presentation, is that these hydrocarbons, from a certain length, so like hydrocarbons from 1 to 5, they're going to exist as gas at room temperature. All right. And from 6 to 10, they're going to be liquid at room temperature, and it's going to go on from there. All right, so let's step across. What are some of the uses that we can have for hydrocarbons that you take from petroleum? So we have acetylene, which is used in gas welding. All right, so we have acetylene. Acetylene is used to weld substances, and cut metal. You can also have these hydrocarbons making polymers, which we're going to get into later on. I'm not going to take my time here, even though I'm going to come back to this another time, because we want to make sure we focus on the reactions today particularly. And there's a whole lot of uses for hydrocarbons. They can be used to make Teflon. Teflon is carbon with a chloride base. It helps you in cookware for non-stick pans. You can also have it in making plastics, where hydrocarbons can be applied again. Carbohydrates. When we eat, the food we eat, the energy we get them from organic compounds as well. Okay, and the list goes on and on. All right, so a lot of these things we're going to be coming back at them, nucleic acids, etc. I'm going to close off this particular PowerPoint presentation, and we're going to look at the one that we really want to take for this time. All right, everybody's cool so far?
Yes.
All right. Satoya, you still there? I had to call her Satoya.
No, why?
Yeah. All right. Good. And Kimani, I ain't even hearing Kimani.
I don't think he's here.
Okay. All right. So what we're looking at today
is.
Oh, he's there. All right. Good.
Yeah.
What we're looking at now is reactions of organic compounds. Based on the homologous series, we're going to be looking at different reactions. I think I placed that on Edmodo, so you should be able to get it. But I'm going to update it as time goes by, because I want to add some more information to it. But you can look at it as it is there now. And I think probably by sometime later in the week, after we finish, I can put a little quiz. All right, I wouldn't be able to do the quizzes today. I wish I could have get it done, but I don't have it finished. But if I get it finished before the end of the day, I would inform you guys if you're interested, and so that you could at least test yourself out. But I want to give you some time before, at least 2 days, to just review your information, and then we can tap in again. All right, so here's what. So hydrocarbons. We know hydrocarbons are compounds made from
Hydrogen.
Carbon and hydrogen.
All right, good. So we have an example of 2 homologous series. We have alkanes and alkenes. Right? We know we have, what else? What are the other homologous series we can have?
Carbon.
Alcohols and propanoic acids.
Right. and alkanoic acids,
Alkanoic acid.
right? And well, there are some
Alkanoic.
others. There are esters and so on and
Esters.
so forth. We're going to get into those as we go on later. So alkene has a general formula of CnH2n plus 2. All right. All right. Alkanes, as we would have known from before, they are saturated hydrocarbons. And this just simply means only single bonds between the carbon atoms. All right. What else? The physical properties of an alkane, well, we know they have the melting point increases with increase in molecular size or the boiling point. They're both going to increase based on the molecular size. And that what we would have observed even from before is as we increase in the number of carbon, the boiling point or the melting point is going to increase. All right. First for alkenes, first four, it should have been 4. 1, 2, 3, and 4, all right, which is met at propan butane. They are gases at room temperature. And from 5 to 16, they are liquids at room temperature. And those that are 17 and above are solids. All right, these are hydrocarbons that are alkanes. All right, now, what are some of the chemical reactions that alkanes undergo? So the first chemical reaction, or one of the main chemical reactions we're going to come up with, is combustion reaction. So what is combustion reaction? Basically, combustion reaction is when a hydrocarbon burns in the presence of oxygen, and as a result, they're going to produce carbon dioxide and water. This process is an exothermic reaction. What does it mean?
Produces heat.
Excellent, right? So it releases a whole lot of energy, all right? We would not have covered this area, but just tacking on it a little bit, what we would observe, there are some compounds that store energy in them. As a matter of fact, all compounds have energy within them. Some require a great amount of energy to break bonds. All right, and and when you break bonds and you form new products, energy is released. All right, now there are some compounds that require very little energy to break bonds. Example, hydrocarbons. They are highly volatile. The compounds are highly reactive, especially in the presence of oxygen with fire. So what happens when you light a fire, which is the energy unique, just a spark, sometimes is enough to ignite and cause an explosion. Why? Because these particular compounds contain a whole lot of energy inside of them. So when the bonds are broken, the amount of energy that is released is a lot, right? So as a result, we refer to them as being exo, which means outside, and thermic, which comes from thermo, which is temperature, which means that the heat is going to be on the outside. So you're going to have heat releasing on the outside. All right. So hydrocarbons, the alkanes, the first reaction they undergo, we call them combustion reactions. And in a combustion reaction, it is important to note that carbon dioxide and water is produced. Always. And if you look at this, I know some people get confused when you see delta H. Delta H is just basically energy it's referring to. And the minus and VE means negative. Instead of writing out the word negative, you put negative. So anytime you have a delta H being negative, it's an exothermic reaction. But we're gonna tackle that when we have better chance, when we are in person the next time. All right. So let's move on. Chemical reactions of alkanes. Some alkanes are, since alkanes are saturated hydrocarbons, they have the maximum number of hydrogen atoms. So what's going to end up happening for them for their reactions? They're going to undergo what we call substitution reactions. So alkanes undergo what we call substitution reactions. Let me get that pointer. So it's very important. So where one of the hydrogen is replaced by a next element. All right, so pin across now. So this is an example of a substitution reaction. So this process is called halogenation. So halogenation is an example of one of the reactions that occur with an alkane. All right. So halogenation, what happens? This reaction is carried out, and this is supposed to be in the presence of UV light, which is from the sun or any light, or at temperatures of 200 degrees Celsius. So in order for this reaction to go, light must be present in the case of an alkane. All right. The reaction, so this one you could realize it with chlorine. So in UV light, it's going to react with the chlorine gas. But when we go down to the bromine, it will react to the bromine, but at a very slow rate, right? It's not very vigorous. Chlorine is a little bit more, but it's less vigorous with bromine. So what's happening here is that one of the hydrogen is replaced by a chlorine. So the chlorine here, one of these chlorine atoms, we have two of them combined here. They're going to take off. One of the hydrogens are going to be replaced with one of the chlorine. So we have CH3 now and a Cl. And now we have the next hydrogen that would have the hydrogen that would have been lost would link up with the next chlorine. All right. So that's what happens in this case. So it's what we refer to as a substitution reaction. Why we call it substitute? Because one is substituting itself for the other. So chlorine had two chlorine molecules before. So what happens? Chlorine reacts with the alkane and substitutes a hydrogen. So it's going to take a hydrogen. Chlorine is going to bind to the hydrocarbon, and the hydrogen that was left would bind to the chlorine that was present. And that's where we have an example of halogenation. All right. Now, it's the main reaction that occurs with alkanes. Now, what I'm going to advise you all, it's very important, and I see you have your concise. Let me see if I can point the page out to you, because you need to know how this reaction runs. So if you could turn on page 137, and you can see the example there, right? And you can see on the concise, it says, in dark, no reaction occurs, because we know that this reaction, the substitution reaction, which is the halogenation, must occur in the presence of UV light. So in bright lights, a rapid reaction. In dim lights, a slow substitution reaction occurs in stages where one hydrogen is replaced by one chlorine atom at a time. So this takes stages. It takes stages in order to get to it. You need to know the stages and the process and the products that you have at each stage. So sometimes they ask you about it. So you take a note of it. Very important. All right. So note and also note that bromine is less vigorous. So if there's no light, it's not going to react with the bromine. Anybody have a question?
No.
Does it react with any other halogens?
Yes, it can react with other halogens, but like say for instance, fluorine, it may be able to react with fluorine, but fluorine kind of fights to bond with other stuff because it's so strongly bonded to other substances. So chlorine is the major one that actually would carry out the reaction, but fluorine can bond as well, and vigorously too.
Okay.
But the note here is that bromine for one does not react with it at vigorous. So what happens, if you notice and you turn to page 138, you will see Similar substitution reactions occur with bromine vapor or bromine solution and with other alkanes. Though the reactions are slower, during the reaction between bromine and any alkane, the color of the bromine slowly fades from red-brown to colorless, all right, in the presence of UV light. This indicates that bromine is being used up in the substitution reaction. So if UV light is present, the reaction will slowly go. If there is no light present, then that reaction is not going to go as it should. It would be at a halt, all right, until light is present. All right, so we're gonna move on to alkenes now. That's alkenes done there already. So what we learn, alkenes undergo what type of reactions? First one was what?
Saturated.
No, the type of reactions. So it is a saturated compound, but there
The
are two
first
types
is
of
combustion.
combustion reaction. And the second reaction is what type of reaction?
Halogenation.
Which is what?
Substitution.
Right.
Substitution.
That's correct. So alkenes can undergo combustion reactions and substitution reactions. What is an example of the substitution reaction it can undergo? Halogenation. All right. What's the example you can give? Chlorine.
Chlorine.
All right. And it must
Be
the conditions that must be
UV
present.
rays.
Right. UV
UV
rays.
rays.
Right.
Or 200 or heat.
Yes,
Heavy.
200 degrees Celsius heat. Right.
Yeah.
Good. So we're moving on to alkenes. So alkenes, they contain a double carbon to carbon bond, right? They are referred to as being unsaturated compounds, right?
Yeah.
So they can hold, which means they can hold more atoms, therefore they undergo addition reactions. One, they have the double bond, which means it's possible for the carbon to take in more atoms. That's what happens with the unsaturated. So they can undergo reactions, but they're not going to undergo substitution reactions. They're going to undergo addition reactions. So they're not going to substitute any element on there. They just add this. So they say, come on in, come on in, come on, join the bond, join the family. That's what happens. So these are just some examples of some alkenes. All right, and as the number of carbons increase, the boiling point would increase. All right, so that's just one part. So type of reaction they undergo addition reactions. All right, so these are a list of addition reactions they can undergo. One is called hydrogenation, another is halogenation, just as alkanes, but maybe they will be in a different way. They can undergo hydration, they can undergo hydrohalogenation, and of course combustion, which is outside of the addition reaction. Combustion reaction is just basically burning in oxygen to form carbon dioxide and water. All right, so this is not an addition reaction, okay? But the others on the top, they are addition reactions. So these are some examples we have. If you look in your concise, you're going to see the list of them from page 138 to 139, all right? Addition of hydrogen is hydrogenation. Addition of halogens is halogenation. You see here, hydrohalogenation is addition of an hydrogen halide, and addition of water is called hydration. And there is a next reaction, which is an oxidation reduction reaction, which we're going to talk later down in this same slide, with acidified potassium manganate solution, and we have polymerization. So you're going to see those in page 139 in your concise. Everyone's with me, right? Just making sure. All right. All right. So like alkanes, alkenes will burn in air to form carbon dioxide and water. Okay. So the same here. Okay. So that's pretty much straightforward. Carbon dioxide and water is produced, as well as a whole lot of energy, because they are exothermic reactions. So hydrogenation. Alkenes will add hydrogen gas to form the alkene. Okay, so you can add hydrogen, react it with hydrogen, and it's going to create an alkane. So yes, you can produce an alkane from an alkene by the process of
hydrogenation.
Right? So this reaction is carried out at 200 degrees Celsius over a metal catalyst, usually nickel. So we usually have the nickel catalyst. You're going to see it there in the same page 138 where you will see it there. So they have 150 degrees Celsius at 5 atmospheres with a nickel catalyst. You all see that in your concise? Should be able to see it there. All right, that's on page 138. All right, so that's one of the addition reaction. So in this case, we have a 2-carbon chain, which is ethene, would react with the hydrogen to form ethane. All right. Yeah, you know, I suppose I have a quizzes on this, you know.
Yeah.
I'm supposed to have a quizzes on this. So one,
So,
yeah.
Excuse, when is the class ending?
What time it is there now? All right, so we would end before 4:30. I'm just running through this here.
Okay, cool.
All right. So where's the application of this particular hydrogenation? One, you have margarine manufacture. So that's butters. So what happens when you can get oils from animals and you can get oils from vegetables? And what happens, the oils that you get from these elements, they tend to have double bonds in them, which means that they would be what? If they have double bonds?
Oh, alkene.
They're going to be
Well,
alkene, or we refer to them as being
unsaturated.
what? Unsaturated.
Unsaturated.
Right. So what happens in the industry, they are going to carry these oils under the process of hydrogenation. So if you take a chance when you're going and you're looking at your products again, and you're going to see hydrogenated vegetable oils, when you see that hydrogenated vegetable oils, it means hydrogen was added, which means that you're going to make them saturated. So they use unsaturated fats or unsaturated oils, which is hydrocarbons, to make saturated oils, which is now going to make them a little bit hard and keep them on the shelf, keep them on the shelf for a longer period of time and these things.
When they do that, this is off topic. When they do that, would they put unsaturated with the but hydrogenated? Would they put that?
Yes, they
Would they
sometimes
put saturated?
Sometimes you will just see them put, they would put the oils there. They will say saturate, they will give the number of fat that it has inside of there. But when you read in the ingredients, you're going to see hydrogenated vegetable oil, or you're going to see hydrogenated oils. You take a note of this, because when they do that, they're going to change the composition of the oil.
So and they could pass it off as being unsaturated, but it is saturated.
They wouldn't say that it is they wouldn't say unsaturated.
Okay.
Because it's not unsaturated anymore. There is no double bond.
It's still it's saturated now.
Right, but they're going to tell you it's vegetable oil.
They wouldn't say anything about being saturated or unsaturated.
Right. So they'll say vegetable oil, but when you read in the ingredients, you're going to see hydrogenated vegetable oil, right? Or hydrogenated fats. All right, so that's something very important.